One will find themselves making meaningful bonds with those they encounter and the friends they connect to. Sometimes these links can feel so strong that individuals feel attached to one another in a way that's beyond regular physicality. But could an argument be made that the feelings of this sort, love, friendship, trust, etc., are partly or wholly influenced by quantum entanglement? First, we need to take a step back and explain the concept more fully. The idea originated in 1935 with none other than Albert Einstein, alongside research associates Boris Podolsky and Nathan Rosen. Their paper imagined two particles that interacted with each other in a way that linked their spatial coordinates and momentum. It was found that by determining either the position or momentum of one system, one could infer the position or momentum of the other. This would then imply that the second particle must have had a definite position and momentum before the measurement had been made. But that would violate one of the fundamental laws of quantum mechanics, the Heisenberg uncertainty principle, which states that it's impossible to know both a particle's exact position and momentum. It's heady science, but Einstein called it the Einstein-Podolsky-Rosen, or EPR, paradox. Following the release of this paper, the renowned physicist Erwin Schrödinger wrote a letter to Einstein, referring to the concept as Verschränkung, which translates into English to mean entanglement. Schrödinger subsequently published two papers on the concept, stating that it was, quote, the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought, end quote. Regardless of being responsible for conceiving the idea, both Einstein and Schrödinger were unhappy with the concept, primarily because it implied that information could be transferred between particles faster than the speed of light. This went directly against Einstein's own theory of general relativity, which postulates that nothing can move faster than light does. It was famously dubbed spooky action at a distance by Einstein, who saw in this early form of entanglement evidence that quantum theory did not provide a complete description of reality. The papers on the EPR paradox generated a lot of attention in the scientific community, but unfortunately at the time no methods existed to put the hypothesis to the test. Following on from it though, in 1964, another physicist, John Stuart Bell, showed that one of EPR's key assumptions, the principle of locality, didn't agree mathematically with quantum theory. To simplify the principle of locality, it basically states that for one object to influence another, it needs to touch that other object. It also means that for an object to travel from one point to another, there has to be a direct connection between the two locations in space. So you can't just teleport from one place to another. And if a theory follows this rule, we call it a local theory. Bell then formulated something called the Bell inequality and stated that if quantum mechanics violated this inequality experimentally, it could not be thought of as a local theory. Not long after this, in 1972, John Clauser and Stuart Friedman pitched an experiment to finally put quantum entanglement to the test. And in doing so, they found clear evidence that two entangled particles are able to transfer information between each other faster than the speed of light, thus showing experimentally that quantum physics doesn't preserve locality, alongside proving quantum entanglement for the first time ever. In turn, this showed that the EPR paradox wasn't really a paradox at all. In fact, entanglement works wonderfully well with the framework of quantum mechanics. While Einstein believed quantum mechanics to be incomplete, and that there were hidden variables responsible for transmitting information beyond the speed of light, in actuality, nothing is being transmitted. The particles are both linked to one another via entanglement, but they are still unable to send signals or objects between each other. To explain this in more simple terms, imagine splitting up a pair of identical socks, putting them in separate packages, and posting them to opposite sides of the earth. From opening the package and looking at the sock therein, the color, size, and shape of the other sock can be inferred. Yet nothing has been transferred between the two socks during this process. Since then, more experiments have successfully shown evidence of entanglement. By this point, there's almost no doubt in the scientific community that the effect is real. Two particles can be entangled no matter how far apart they are, and making measurements of one particle's physical properties conveys information about the other. For example, you can measure their position, spin, and momentum, among other things, and there will be appropriate correlations. There are various mechanisms that can be responsible for creating entangled particle pairs, but generally all particles that interact physically can become entangled with one another. An example of this is a light source emitting two photons simultaneously. The orientation of their oscillations will be completely random when measured. but an entangled pair will always have matching orientations. So if one photon is measured to be oscillating vertically, its partner particle will also be oscillating vertically when measured. And so to get back to our title question, perhaps surprisingly, one place where scientists predict entanglement to be common is within our very own brains. Some make the argument that the immense power of our brains arises from quantum processes, including entanglement. In 2022, researchers from the Trinity College Institute of Neuroscience claimed to have successfully observed entanglement within the brain, mediated by consciousness-related functions. This experiment was done using an MRI machine, powerful enough to measure the spins of protons from water in the brain. The research implies that the way our brains function could not be wholly described by classical physics, and that they could instead be powerful quantum systems. While these results are an excellent starting point, as of writing, they've not been confirmed by other researchers. There's a possibility that the observed effects were caused by a separate process. Currently, how our brain works is one of the biggest mysteries known to humanity. Furthering our understanding of the human mind would have numerous applications, though. For example, it could help advance our understanding of quantum computing, and it will definitely aid us in knowing how to maintain and heal our minds. So there's evidence to suggest entanglement is happening within our own brains. But what about between two separate brains? Currently, there's no active research on the topic, and it's likely to stay that way until we figure out how entanglement plays a part in individual people. Regardless, plenty of speculation has been made as to whether the effect has a role in human connections, especially love. The two concepts are broadly unrelated, but harbor a number of parallels. When we have a strong connection to our partner, it can feel like our minds are entangled, as if they're separate elements of the same state of consciousness. Currently, as things stand, the quantum entanglement of microscopic particles is incredibly unlikely to produce a macroscopic effect that can alter human emotions. Certainly, it is possible for atoms in two separate brains to become entangled, but the chances of this happening between you and the love of your life are as high as the chances of elements in your brain being entangled with a distant asteroid. And even if the minds of a couple were entangled, it would not allow for information transfer or the strengthening of romantic bonds. It would simply mean that if scientists could take measurements of one person's subatomic particles, they could infer properties about the other person's as a result. In conclusion, realistically, entanglement produces effects that are observed exclusively with subatomic particles. It is therefore theoretically conceivable that systems on our scale can become completely entangled with one another, but to get there would require a great deal of isolation and control. The concept of entanglement remains one of the most interesting and exciting fields in modern-day physics, and a substantial amount of poetic parallels can be drawn between the connection of two particles and the bonding of two people. Unfortunately, the current state of technology isn't capable of verifying a link between humans and the quantum world. But irrespective of this, it's still worthwhile to appreciate the beauty of the similarities between the two.